Okay, this is a solution for 2.863, and in this problem, you're asked to prove that a derivative of an even function is odd and the derivative of an odd function is even. One of these is actually easier than the other, but part A tends to be the more challenging one. So let's go ahead and take a look at part A here. Let's suppose that f is even, which just implies that f of negative x here is equal to f of x. And we'll then take a look at the derivative of f. Now, what we want to show is that the derivative of f is going to be an odd function. Well, if we want to show that the derivative of f is an odd function, then we want to show that when we take the derivative of f of negative x, it returns a negative derivative of f of x. Or in other words, that the opposite of the derivative of negative x is just equal to the derivative of f with respect to x. So this is actually the version I'm going to use here. I'm going to go ahead and just take a look at the derivative of f first. And then I'm going to hopefully transform that into the opposite of the derivative of negative x. So I always start with kind of a roadmap of where I want to go. So we happen to know that the derivative of f of x is just the limit as h approaches 0 of f of x plus h minus f of x all over h. And I know that since f is even, the limit as h approaches 0 of f of the opposite of x plus h minus f of the opposite of x all over h. So that is just coming from the fact that we know that f is an even function, that f of an argument is the same as f of opposite of the argument. I'm going to do some distribution here. This is the limit as h is approaching 0 of f of negative x minus h minus f of negative x all over h. And now what I'm going to do is a little bit of a trick. Now what I'm going to do is make a little move that some people will have a hard time with. So what I'm going to do is make a different variable here. I'm going to say let h bar equal the opposite of h. And sorry, that's just a bunch of email coming in. It's Monday morning, so everybody wants to email this early in the morning. So let's see. If I make that substitution, if h is going to 0, then h bar also is going to 0. So that means that I'm still taking the limit of something going to 0. H downstairs is replaced with h bar, which, by the way, that means h is the opposite of h bar. So let me go ahead and write that down. And upstairs, I have f of negative x, and a negative h, again, is just a positive h bar minus f of negative x. Let me factor the negative out front from that denominator, and I get the negative limit as h bar is approaching 0 of f of negative x plus h bar minus f of negative x all over h bar. And that is actually the definition of derivative. It's the opposite of the derivative of f evaluated not at x, actually, but at negative x. Otherwise, it's exactly the same as the definition of the derivative. So this is just the opposite of the derivative of f evaluated at negative x. Now remember what we wanted to show. We wanted to show that the derivative, let me highlight that, of negative x, I don't know why I highlighted so strongly, but the derivative of f at negative x is the same thing as negative derivative of f of x. Or in other words, we want to show that the derivative of f at x is the same thing as the opposite of the derivative of f at negative x. And we've shown that the derivative of f at x is actually the opposite of the derivative of f at negative x. That's actually the more challenging of the two parts. But that's done. Now we just go ahead and do it for an odd function. So let me scroll down a little bit. We're going to assume that f is odd. So if f is odd, I'll use actually a different letter here. I'll use g. If g is an odd function, then g of negative x is negative g of x. All right, so let's go ahead and do this. Oh, by the way, that will imply that we want to show that g of x, so actually we want to show the derivative of an odd function. Here's an odd function, sorry. The derivative of odd functions is even. So we want to show that, let me write this down. In blue, want to show that the derivative of an odd function is an even function. That's what we want to show. So we want to show that g prime of x is just g prime of negative x. Okay. And this one, actually, I'm going to go ahead and start with, because the previous proof, I actually started with working with f prime of x, and I ended with a negative f prime of negative x. This time I'll go the opposite direction just to show you how it's done. I'm going to start with g prime of negative x, and I'm going to end with g prime of x, just to show you how that's done. Okay, so g prime of negative x. Well, that's the defined to be the limit as h is approaching 0 of g of opposite of x plus h. Oops, that's not true. It's opposite of x and then plus h minus g, evaluate the opposite of x, all over h. That is g prime at negative x. And remember, we want to show that this is g prime of x. So what I'm going to do is, since we know that g is odd, I'm going to factor a negative out of both of those functions. It's not really factoring, it's actually using the property of g being odd, but it looks to most people as if you're factoring. And when you do that, maybe I should do it in 2 steps just to really showcase it. When you do that, you get this, g of negative x minus h, and then minus, I'll again just do it in 2 steps here so you can really see it, g of negative x all over h. And now I'm going to take these negatives and use the fact that g is odd. So I'm going to pull these negatives, oops, wrong one there. I'll pull these negatives here outside of the function. So when I do that, I get the limit as h goes to 0 of the opposite of g of x minus h plus g of x all over h. And I'll factor the negative off of the numerator. So the negative will, actually, what I'm going to do is pull that negative. I'm going to not, instead of pulling it out of the entire limit, I'm going to shove the negative into the denominator. So the limit as h goes to 0 of g of x minus h plus g of x, oops, factoring the negative off both, so it'd be minus g of x all over negative h. Now, that is very, very close to the derivative of g, except that the derivative of g would be g of x plus h minus g of x over positive h. So I'm going to do the same trick that I did before. I'm going to let h bar equal the opposite of h, which will imply that as h goes to 0, h bar will go to 0. And wherever I see a negative h, I get to replace it with an h bar. I wrote that as a vector. Sorry about that. There we go. So here we go. Let's do that. So the limit, still we're going to let h bar now go to 0. And we'll have g of x, instead of a negative h, we'll have plus h bar minus g of x. All over, instead of a negative h downstairs, we'll have an h bar. And that is actually the derivative of g at x. So we've successfully shown that the derivative of g at negative x is the same thing as the derivative of g at positive x, or in other words, that g prime is even. And to be complete, I should have said in the previous proof here that f prime is odd.